Beneath the serene countryside on the border of France and Switzerland lies the largest and most powerful machine ever built by humanity. This is the Large Hadron Collider, or LHC, a magnificent 27-kilometer ring of superconducting magnets and advanced particle detectors. It's a place where we recreate the conditions that existed just a fraction of a second after the Big Bang. Its purpose is not just to see what happens, but to ask the most fundamental questions we can conceive. What is the universe made of? What are the basic rules that govern everything we see, from the smallest quark to the largest galaxy? It is a testament to our innate curiosity and our relentless drive to understand our place in the cosmos. The LHC works by accelerating two beams of particles, usually protons, in opposite directions to nearly the speed of light. Guided by thousands of powerful magnets, these beams are then steered to cross paths at specific points, causing them to collide with immense energy. These collisions are like tiny, controlled Big Bangs, unleashing a shower of new, often exotic particles. Giant, cathedral-sized detectors like ATLAS and CMS act as powerful cameras, meticulously tracking the paths, energies, and identities of every particle that emerges from the fireballs of these collisions. By analyzing this data, physicists can piece together the hidden laws of nature, testing our theories and searching for new phenomena. This extraordinary machine has already delivered profound insights into the workings of our universe. Its most famous discovery in 2012 was the Higgs boson, the long-sought particle that gives other fundamental particles their mass. Its existence confirmed a cornerstone of the Standard Model of particle physics, our best current description of the universe's fundamental building blocks and forces. The discovery was a monumental achievement, earning a Nobel Prize and completing a picture of reality decades in the making. But science never stands still. Every answer we find only leads to deeper, more fascinating questions about the universe's remaining mysteries. Why is this so important? Because the Standard Model, for all its success, is incomplete. It doesn't explain the persistent pull of gravity, nor can it tell us what the mysterious dark matter that holds our galaxies together is made of. It leaves vast territories of our cosmic map completely blank. The LHC is our most powerful tool for exploring these unknown lands. It's a journey into the very fabric of reality, pushing the boundaries of technology and knowledge. Every collision, every piece of data, brings us one step closer to a more complete understanding of the universe and our existence within it. To peer deeper into the universe's secrets, scientists at CERN realized they needed more than just high energy. They needed more data. Imagine you're trying to find a single, specific grain of white sand on an enormous black beach. The LHC, in its current form, is like having a powerful but small flashlight to search. The High Luminosity Large Hadron Collider, or HLLHC, is the ambitious project to upgrade that flashlight to a giant stadium floodlight. The goal is to dramatically increase the number of particle collisions, a property physicists call luminosity. By increasing the luminosity tenfold, we increase our chances of witnessing incredibly rare events that could hold the key to new physics. This increase in luminosity means the HLLHC will generate a staggering amount of data, far more than ever before. Over its planned operational period from 2030 to 2041, it aims to record about 15 times more collision data than the LHC has produced in its entire history. This vast dataset will allow physicists to study known particles like the Higgs boson with unprecedented precision. We can look for subtle deviations from our predictions, which could be the first hints of new particles or forces. It's a bit like taking a blurry photograph and bringing it into razor-sharp focus. We might see details we never knew were there, completely changing our perspective. The primary scientific objective is to push beyond the boundaries of the Standard Model. While finding the Higgs boson was a triumph, it also opened up new avenues of inquiry. The HLLHC will enable us to search for answers to some of the biggest puzzles in science. Could we find the particles that make up dark matter, the invisible substance that constitutes about 27% of the universe? Could we uncover evidence for new dimensions of space, or understand why there is so much more matter than antimatter? These are the profound questions that the high luminosity upgrade is designed to tackle by providing a flood of new collision events to analyze. Essentially, the HLLHC is not just an upgrade, it's a transformation. It represents a shift in strategy from simply reaching higher energies to meticulously sifting through a mountain of high-quality data. By making the particle beams denser and squeezing them more tightly at the collision points, the rate of interactions will soar. This ensures that for every second the machine is running, the probability of making a groundbreaking discovery is magnified. It is a bold leap forward, promising a new era of exploration at the energy frontier and a deeper understanding of the fundamental laws of nature. At the very core of this ambitious upgrade are the new, incredibly powerful, superconducting magnets. These are the technological marvels that make the high-luminosity LHC possible. Weighing up to 20 tons each, these magnets are engineering giants, crafted from an innovative niobium tin alloy. Their job is to perform a crucial task, to focus the particle beams into a space thinner than a human hair just before they collide. The stronger the magnetic field, the tighter the squeeze, and the greater the chance of a head-on collision. These new magnets can generate a field of 11.3 Tesla, a significant leap from the 8.3 Tesla magnets currently in use. To understand why these magnets must be so powerful and so cold, we need to talk about superconductivity. In a normal wire, like the copper in your home's wiring, electricity faces resistance, which generates heat and wastes energy. But when certain materials are cooled to extremely low temperatures, they enter a state called superconductivity, where electrical resistance vanishes completely. This allows a current to flow forever without any energy loss. For the niobium tin magnets at CERN, this magical state is achieved at a mind-bogglingly cold 1.9 Kelvin, which is minus 271.3 degrees Celsius. That's colder than the depths of outer space. Achieving and maintaining this incredible cold is a monumental engineering feat in itself. The magnets are cooled using superfluid helium, a bizarre state of matter that flows without any friction and can conduct heat with perfect efficiency. This liquid helium circulates through a complex network of cryogenic pipes that surround the magnets, keeping them at their precise operating temperature. The entire system is a masterpiece of cryogenics, requiring enormous refrigerators and thousands of sensors to ensure that these technological titans remain in their superconducting state, ready to wrangle the energetic particle beams with their immense magnetic grip. The sheer scale of these components presents a unique challenge. Each 20-ton magnet must be transported and installed with millimeter-perfect precision deep underground in the LHC tunnel. This is delicate, painstaking work, where the slightest error could have significant consequences. The magnets are not just lumps of metal, they are intricate instruments, the result of years of research and development by an international collaboration of scientists and engineers. They are the powerful heart of the upgraded machine, and their chilling performance is what will drive the next decade of discovery in particle physics. Before these colossal magnets can be installed in the main LHC tunnel, every component must be rigorously tested to ensure it can withstand the extreme operating conditions. To do this, CERN has built a full-scale replica of the new accelerator sections, a remarkable test facility known as the IT string. This allows engineers and scientists to assemble, cool down, and power up the entire system in a controlled environment above ground. It's a complete dress rehearsal for the real installation, allowing the team to iron out any unforeseen issues and perfect their procedures before taking on the real thing deep underground. The IT string is more than just a test bed, it's a crucial training ground. Teams from around the world are learning how to handle the complex assembly, which involves making around 70 highly specialized interconnections to maintain the superconducting circuits. The power supply line alone must carry over 100,000 amperes of current, an immense amount of electrical energy. By practicing on the IT string, crews gain invaluable hands-on experience, ensuring the final installation during the LHC's next long shutdown period proceeds as smoothly and efficiently as possible. This meticulous preparation is vital for the success of a project of this complexity and scale. The successful operation of the IT string, with its first power-up expected by the end of 2025, will be a huge milestone, validating years of design and manufacturing work. It represents the culmination of a massive international effort, with contributions from institutions across the globe. This kind of science is simply too big, too complex, and too expensive for any single nation to undertake alone. It is a powerful example of what humanity can achieve when we pool our knowledge, resources, and ambition towards a common goal: the pursuit of fundamental knowledge for the benefit of all. Ultimately, these heroic efforts, The chilling of 20-ton magnets and the boosting of particle collisions are all for one purpose: to shed light on the darkest corners of our universe. The high-luminosity LHC promises to give us a clearer view of the subatomic world, potentially revealing new particles, new forces, and a new understanding of the cosmos. Whether we discover the nature of dark matter or uncover flaws in our most cherished theories, the journey itself pushes the limits of technology and inspires a new generation of thinkers. It is a grand adventure, written in the language of physics, that continues our timeless quest to understand the universe and our place within it.